So, if you've ever seen a photo of an oil field, or maybe you've driven through the plains of Texas or Alberta, you've undoubtedly seen this iconic silhouette, right? The classic nodding donkey against a sunrise. Well, welcome to this explainer. There are actually over 1 million of these beam pumping units nodding away worldwide. But today, we're going to completely change how you look at them. We're going to look right past that famous silhouette and learn how to actually read this machine.
Okay, let's just dive right into this. I want to immediately shatter a baseline assumption you might have. That massive steel structure you see up on the surface, it isn't actually a pump at all. Nope, it is simply an arm. Think of it as a very, very patient arm, completely designed to pull a long steel rope out of the earth and then let it back down. Up to 8 times a minute, without stopping, for maybe 30 straight years.
Now you're probably wondering, if that nodding donkey on the surface isn't the pump, where exactly is the pump? Well, it's located a staggering 2,000 feet straight down in the earth. Sometimes it's even deeper than that. The surface machine's only real job is to provide the mechanical muscle to reach way down into that darkness and operate the hidden pump. So how exactly do we send power 2,000 feet underground? It requires a very specific chain of kinetic energy. Step 1 is our prime mover. This is usually an electric motor or a gas engine, and it provides the raw power. It turns a gearbox that acts as a speed reducer. Then that gearbox turns a crank arm in a continuous circle. Next, a part called the pitman connects that rotating crank to the horizontal walking beam, forcing it to rock up and down. Finally, the front of that beam pulls on the polished rod, which goes straight into the ground. Basically, we're taking rotary motion in at one end and pushing straight up and down rod motion out at the other.
But here's the fundamental engineering problem we run into. On one end, we have a rotating crank that naturally wants to move things in a circle, right? But on the other end, we have our polished rod and the massive steel rod string attached to it. That steel string absolutely must be pulled dead straight up out of the well. If that rod gets pulled even slightly sideways in a circular arc, it's going to rub right through the solid metal wellhead at the surface. You just cannot pull a straight string with a circular motion without breaking something.
The brilliant solution to this geometry problem is a piece of hardware called the horse head. When you look at one of these units, the front part looks, well, exactly like the curved head of a horse. But that curve isn't just decoration to make the machine look nice. It's actually a neat, incredibly exact engineering trick. As the walking beam rocks in its arc, a flexible steel cable, called a bridle, rolls right over the curved face of that horse head. Because of that specific geometry, the polished rod hanging from the bridle is kept perfectly vertical through the entire up and down stroke. That single curved piece of steel literally makes the whole shebang possible. So why do we even need these patient arms everywhere in the first place? Well, these units are the absolute workhorses for what the industry calls onshore stripper wells. These are mature wells that produce anywhere from just a couple of barrels to maybe a few hundred barrels of oil a day. The key factor here is that the natural reservoir pressure deep underground is simply too weak to push the oil to the surface on its own anymore. The well has essentially ceased to flow naturally. It needs a little help. It needs artificial lift.
So how does that artificial lift actually work? Let's take a look at the downhole mechanics happening thousands of feet below. The subsurface sucker rod pump uses these clever little ball and seat valves. On the upstroke, the valve on the moving plunger, we call that the traveling valve, closes. This traps the fluid above it. At the exact same time, the standing valve at the very bottom opens to let more fluid into the pump barrel. The surface arm then lifts that whole fluid column. Now on the downstroke, the traveling valve opens up, allowing the plunger to literally fall down through the fluid to reload, while the standing valve shuts tight so the oil doesn't just drain back away. Every single barrel of oil arrives at the surface just like this, one stroke at a time.
What's really fascinating here is the math behind that production. To calculate how many barrels they'll get per day, drillers use a formula that factors in variables like pump efficiency, the area of the plunger, and the strokes per minute. But honestly, it's the practical ranges that really tell the story. A typical unit operates between 6 and 12 strokes per minute. And the stroke length, which is how far that polished rod actually travels up and down, ranges from a short 40-inch pull all the way to a massive 192-inch pull.
And that brings us to a brilliant mathematical loophole. Longer stroke equals more oil, with absolutely no extra speed. Think about it. If you want to pull more oil out of the ground, speeding up the machine past 12 strokes a minute will literally just wear out the parts and completely damage the steel rods. But if you simply double the stroke length, boom, you double your daily production without having to speed up the machinery even a little bit. This is exactly why you'll see those massive long-stroke pumping units towering over certain oil fields.
All right, I need to shift our tone to something incredibly serious for a second. On the crank arms of the machine, there are massive steel blocks called counterweights, and they weigh several tons. As the crank turns, they swing through a low arc right at head height. Because of all that built-up momentum, they absolutely cannot be stopped instantly, and they give zero warning before they swing. Most dangerously, though, a unit that looks completely stopped might actually just be paused on a timer, ready to restart in total silence. You must never, ever step inside the counterweight arc without physically locking the brake and electrically isolating the motor. It is a lethal hazard.
Okay, to really ground this massive industrial machine in perspective, we can look at the oldest analogy there is. A beam pumping unit is really just a mechanized version of drawing water from a village well with a rope and a bucket. You pull the rope up, the bucket brings the liquid. You lower it, the bucket refills. The nodding donkey does this exact same motion, just at an industrial scale. And those massive, dangerous counterweights we just talked about, they exist to balance the entire system. They store energy on the downstroke and then give it back on the upstroke. Because they perfectly balance the heavy weight of the steel rods hanging deep in the well, the motor barely even has to fight gravity. It's just a beautifully balanced rope and bucket.
So the crucial point I want to leave you with today is a simple question. You didn't just learn what this machine is called. You learned how it actually works. You understand the horsehead's geometry now. You understand the clever math of stroke lengths. You understand the sheer, lethal force of the counterweight storing energy. Next time you see a nodding donkey on the horizon, will you just recognize it? Or will you read the machine? Because now you actually have the tools to truly read the oil field.